Good evening, everyone. My name is Rajdeep, and welcome to this talk. I think this is the last talk before the tea break, so I'll try to finish it on time. Uh, as the title says, I will be presenting about differentiation engines and why this is behind the AI responses. Because if you see a common LCM behind all the different, deep learning frameworks, you can find one thing that is common, that is the differentiate your loss functions, your optimizers basically, and minimize the way to get get the model trained. So before starting with the agenda, let me talk a bit about myself. Uh, I am currently a research associate. That's a research university in India. Uh, Currently, I'm working on two projects. One is drones as a service, and second is we are trying to improve the latency of fast frameworks. And I love working at the intersection of software engineering, computer vision, and robotics. And in my past life, I was a SP3. I'm feeling like that company called Co. So at a professional level, I have been working with learning frameworks very recently, and that too in the application capacity. I come from a engineering background. So what intrigued me is how they are implemented behind the scenes. That's what made me present this talk. Uh, so, end of the talk, I'll try to go about calculus basics, derivatives, gradients. So throughout the talk, I won't be trying to get deeper into the maths involved. The focus will mostly be around how these are implemented in the frameworks rather than the maths behind it through all. So that is calculus 101. And then the second topic will be different type of differentiation. So I'll let you through numerical, symbolic, and automatic differentiation, and how automatic differentiation is something that a lot of deep learning frameworks have converged to. So yeah, there's that. And then after that, we'll see how these can be implemented. There are two types. One is source code transformation, one is operator overloading. So again, the major deep learning frameworks are working using the operator overloading. But there are a few projects that tried source code transformation that were interesting by the group. So we'll try to dive into it also. And yeah, so just to be setting the expectation here, what I want covering Jacobians, Hessians, dual numbers. So if you are already familiar with those won't be covered because these get math heavy very quickly. The second thing I won't be covering is Julia. So Julia is a language that has a lot of work done in the decision scientific computing world. I'll try to keep the focus on Python and especially in the deep learning ecosystem, not the scientific computing ecosystem as such. And there's a lot of research going on in the automatic differentiation field itself. I'll try not to go into that. Uh, by the end, so by the end of the talk, uh, the goal is to get you excited about the internals of deep learning frameworks, and we will see frameworks with the eye of differentiation engines or how they're implemented, rather than just creating a new CNN or a LSTM with them. Uh, so starting from the first topic, what is a derivative? So a derivative is basically a calculus concept that gives you a rate of change of a function. So to be exact, if a function, let's f8, that is dependent on a variable x. So when you tweak x, how much does the function change? That is what is given to you by the derivative. And that, let's say this is a triangle with x as its base, y as its height, and you make a small change dx to the how the height of triangle, that is y, changes. This is what is derivative. Uh, Yeah, for a very small change in x, y changes by dy, and when you say dy by dx, that is the dx. And this doesn't have to be limited to a single variable. The function can be dependent two variables, three variables, x, y, z, and in case of a deep learning framework, it can basically depend on millions of parameters. Um, yeah. So this is a, let's say, a function fx that is x squared plus pi plus dx e power z. That is so. What is a gradient? To have, so how does the concept of derivative goes into gradient? Oh, goes into the derivative. To understand, you have to understand what a gradient is. So gradient is also a rate of change of function with respect to some other variable. But rather than having a single variable or two variables, we deal with vectors as in deep learning vectors. Let's say you take a multivariate function fx, which is x power 2 plus y power 2. We want to understand how the function changes with nudges to both x and y. This is where gradients come into the picture, like x and y, and how they are defined. This is a mathematical symbol called nabla. When you say nabla of f, you are making a vector of partial derivatives of the function with respect to each of the independent variables. So without going much deeper into the maths involved, Jacobians and all, that is only thing you need to know. And the gradients is what gives you the direction of the highest change. So if you heard the word gradient, you thought about gradient descent. Uh, you might not be entirely wrong. That is what exactly gradient does in machine learning or deep learning. If I give you a 10,000 feet view of the algorithm, so let's say you have a function which has to be converged, right? You start with some random value of x and you try to tweak x such that your function f, uh, which can be a loss function, goes down in value. So how you do is you randomly initialize the model with biases, then you calculate the loss function that needs to be minimized, and then you go back and calculate the gradient vector like, with all the all the parameters of the function. What can you tweak which will change the loss to be a little less in each iteration? And in terms of machine learning, what you do is in the gradients you add a learning rate so that you don't very quickly converge or something. You go it slowly. That is what a gradient descent algorithm is basically. Uh, then comes the differentiation in this part. So this is the crux of the talk, where we actually try to understand how different ways to implement differentiation and gradient calculation. Just to be clear, differentiation engines have a bigger place in the scientific computing ecosystem. They are not only limited to deep learning. If you're into aerospace engineering or fluid dynamics, you can find differentiation engines everywhere. But the focus of the talk is they fit in the deep learning space. So I'll try to go through all the different types of uh, differentiation possible and will pro cons based on how they fit into the deep learning ecosystem or the other. Yeah. So one thing is if you have been following, let's say, large language models like ChatGPT, Llama, or anything, you'll know that the monopoly params can go from few millions to a lot of billions. So the differentiation engine that needs to calculate the it should be uh, designed in such a way that it can act on a large number of inputs. Where the output is let's say one scalar value or a few scalar values. So the implementation should be second. Yeah, the implementation should be fast, memory efficient, and correct. That is the goal of the engine. Yeah. So there are actually three ways to actually differentiate, but I have written four because manual is here to understand uh, how you can actually manually calculate the different derivative of a function, but it's not something that you use or find in any of the deep learning framework. Yeah, there are three major ways. One is numerical, one is symbolic, and one is automatic. In recent developments, you'll find all the major frameworks like PyTorch, TensorFlow, JAX. Everyone has kind of converged towards automatic differentiation. We'll go through why that is the case and see why the numerical and symbolic doesn't fit into that use case very well and where it's actually useful. Yeah. Starting with manual differentiation, just to get the stage. This is the quickest and simplest way you can do differentiation. Let's say you have this is useful such in any domain, but just to showcase it, let's say you have a function fx that is dependent on x to the power 2 plus exponent of x. So let's say you define the function in the Python. It's using numpy exponential and then basic Python power operator. If you want to differentiate, what you'll do is you will use the basic differentiation rules and you'll find the f prime. The power goes into the front and subtracts once, you will get to 2x plus 3x. You can actually just write on the function with f prime and then code that also. So it's not very useful as such, but when you are, let's say, trying to validate automatic differentiation engine or some other one, this can be a good tool. But yeah, it's not for serious work. So the next one is called symbolic differentiation. This is the computer version of hand-derived manual derivatives. Whatever you just go the last slide, you saw that. So you can basically convert that using something called SymPy. Yeah, so simple Python that helps you do the symbolic differentiation. This works in expression level. So what do I mean by that? You won't be manipulating, say, using some finite difference or anything. You'll have an expression. You'll define, let's say, I have a variable called x, I have a variable called y, how they are related to make a function called fx. And what the SymPy will give you is, it will take your expression as input, it will give you an expression as output. That is technically the derivative of your expression. So you can go as deeper as you want into the SymPy, it will give the correct answers. But I'll stick to a basic example where, let's say, this x, I define inputs, symbols, exponential, and the diff from library called SymPy. I define a symbol called x. So everything in SymPy is basically overloaded, as in it's part of the symbol class, or it can be part of the x class or add class. Like each of the operator is defined in the SymPy. So let's say you have defined a x symbol, and now you tell it to x to the power 2 plus exponential of x. You define a variable called fx. And you take the diff function from SymPy, you pass in your fx, and what you get in the df dx variable is the actual output that is for the last slide. Yeah. So what is happening under the hood? You can basically import something called SCPR, which is string representation of any of the SymPy object to understand what is happening. So if you print the X, it's an object instance of class symbol. And when you print the fx, you see it's just a few simplification of a symbol class that pass to the power class, pass to the add class. So these are all SymPy object. What are the limitations of that? So when you're using SymPy, you are limited to closed form expression. And to a mean closed form expression is you can't do a while loop or a for loop or if condition. So as some model has to be timed for the differentiation, you can't technically use SymPy or for that matter other types of SymPy. You have to get into the automatic differentiation only. So another problem that is very infamous while using symbolic differentiation is something called expression swing. So let's say you have a function hx that is dependent on two functions multiplied together. So if you know the basic multiplication rules of calculus, you'll see if you differentiate this function with respect to the differentiate hx, you have to do a f prime of x then multiply it by gx, then do a addition of g prime of x and fx. And let's say this fx and gx, they are also some sort of some function that are multiplication of function. So these quickly add up. Let's say the function was output of a neuron, which was wx plus b, and then that is passed to a exponential log function, which is can be a kind of what is this non-linearity. So what you find is your output expression will quickly, actually exponentially increase in size as compared to input expressions. This was x1, w1, p1, three variables. Then you define w2, p2. Function one is just log of 1 plus exponential of w1 into x1 plus b1. And then your, let's say, output of first neuron, your f1. And then you pass it to the output or to input out to the second neuron. So if you print these while differentiating, you'll see this expression is first of all much larger than the first expression. Second of all, you see a lot of the intermediate steps are actually duplicate of. So exponential expressions will the symbolic differentiation will not be very useful as such, in terms of deep learning. The second thing that we can do is numerical differentiation. So numerical differentiation works on the standard limit definition of derivatives. That is, the fundamental derivative is just the rate of change of function when the input parameter is tweaked, right? So these are all finite differences. So what you do, what the limit definition says is, let's say you have a function, you value at exactly or in more than 2 or 3 places. At first at fx, and then you increase the x very small amount, h, where h is almost tending to 0, and then you take the difference and divide by the step size. If you remember the maths, this is also called a tangent of a line at x. This which is basically rise over the how much the function increase with the run of x. So, but in reality, let's say you in neural networks or something, you're working on tensors and not scalars as such. There are a few changes that you have to do to the function. We won't get to that because that after that also numerical differentiation is not something that is in the frameworks. The time complexity is one of the major concerns which stops the numerical differentiation for being implemented in PyTorch or something. Because for each function, let's say, you have to create the derivative of each of the input, which basically goes to complexity of O n. And let's say you have a billion parameters that doesn't scale, right? So this graph showcase what this equation basically trying to describe, that at each of the this, so let's say this is a function fx, at any 2 points which is a very small difference h, try to pass a tangent and you figure out the difference between these 2 points and you approximate the derivative of that function. Now we come into the automatic differentiation, that is currently the kind of the de facto, you can say, in all the deep learning frameworks, as well as a lot of standard computing frameworks. So what automatic differentiation do is we numerically evaluate the derivative of function, and it guarantees a precision similar to the symbolic differentiation. This means you are not limited to closed form analytical solution as you saw in symbolic, because we are not dealing with equation or the function. You are actually calculating it numerically. So we'll keep calling it AD because that automatic differentiation is a big word to say again and again. So this takes advantages of 3 properties. So any function is can be composed, using basic elementary operations like addition, subtraction, multiplication, or division, and these all have no derivatives. And in case there are non-primitive operations also, like a cos, sine, or exponential, these also come with the well-defined derivatives. And the third, that is the main part that enables ADA, is chain rule. So what chain rule just is, uh, if you want to find derivative of a composite function, let's say, and composite function is basically a function that can be composed from a function. Let's say you have a function called cos x, and fx is cos x, and another function gx, which is x, and you want to find derivative of f of g of x. So what you can do is you can differentiate fx first with respect to gx, and then differentiate gx with respect to x. This will give you the derivative of the whole function with respect to x. This is the key enabler of differentiation as we'll see very quickly. So there are two flavors available for AD. One is called forward mode, one is called reverse mode. So in the forward mode, you can basically say the forward mode is a kind of symbolic differentiation only, but in the sense that the equation is broken down into multiple intermediate frameworks, and they are organized in such a way that they can be reused. So this basically fixes one problem of the symbolic differentiation, and evaluation trace is created. So let's say you have a function which is a multivariate function. It's dependent on x as well as y. So what you do is you convert your x plus y as an intermediate representation, which is called a. Then you do same for y into 3, which is b. And then what you say is the function will define as a multiplied by b. And when you want to differentiate, let's say f with respect to x, what you do is you do partial derivative of x with respect to a, and then multiply that with the partial derivative of a with respect to x. And similarly, you can do the same for y also. So you do a df by dy. To get the df by dy, you do a dA and dy. So in terms of visually visualizing it, how does that work? This is we are trying to find the approximation of the gradient of fx at x equals to 1, y equals to 2. As you see, the a is x plus y. So what we have is x and y. We add both of them, and at the same time we have y. This should be multiplication actually. So yeah, and then you do the same thing for a and b. You multiply a and b, and finally f. So from there you can basically trace back the derivatives. So the derivative of df with respect to itself is 1, and with respect, let's say, to a, so df by da essentially falls down to be y, because df by so yeah, you go back from df, you find df by da, and then you find dx. And in case you want to find the derivative with respect to y, go say dx to b, b. In a sense, forward differentiation is very similar to symbolic differentiation. It's just that it's organized in a way that is intermediate results are given, then shared between the main contribution and the derivative. And how we implement this is with a combination of primers and gens. What I mean by that is, at each forward pass of the graph, what you do is you send the value of a and b, let's say, as well as you send the value of the derivative of a with respect to the function, the derivative of function with respect to a, as well as to b, and the intermediate value. So primers are the actual value of the variables, and tangents are the actual value of the tangents are the derivatives of the intermediate variables. In a single pass, you get the output as well as the derivative of the function. But uh, so forward mode is also not very useful in different contexts, because if you are familiar with Jacobian vectors, forward mode gives you each column in each iteration. What does that mean is, for each of the parameter, input parameter, you have to do multiple passes to find the derivative of that function. To actually overcome that, there is something called reverse mode. This what is actually being implemented with all the frameworks, PyTorch, TensorFlow, JAX, and all. So the derivatives, instead of starting from the bottom of the graph and going towards the main function, which is the loss function, it's the reverse. The derivatives are propagated backwards. So then the forward on dependencies of the expressions are stored, and not the derivatives as such. And when the forward pass is complete, forward path compute the partial derivative of output function with respect to each of the intermediate variables is calculated. And these are called adjoint. So yeah. So why this is preferred over the forward mode is because by in each iteration of a single loss function, you can calculate a gradient for all the intermediate variables as well as all the input variables, thus making it much more efficient in terms. So in terms of frameworks, you'll find a few different frameworks, and this graph is available on the project called Google Tangent. There was an experimental project, and they very well define what are the different spectrum of frameworks available in the different concepts. So if you do the see the model is a data structure. What do I mean by that? If you have used TensorFlow 1.0, you'll know that instead of putting the Python itself, you create a graph and then you do a session.run where the graph of all internet operation is run at once. This was TensorFlow 1.0 as well as Torch and Cafe. And in the right spectrum, Python source code is the model. So if you have used TensorFlow 2.0 with eager mode or PyTorch or AutoGrad, what you do is basically you write the code in the Python itself, and what they do is they do something operator overload. But after each operation, let's say you multiply two variables, your that class of the variable stores your intermediate derivative also. So this is the Python source code. And what the project Tangent does is they try to model as a code in a item order. So when you use PyTorch, everything is calculated in the runtime. So as you are iterating or let's say doing a if else your variable class gets mutated to store the state of new derivative. But tangent does that ahead of time. So what we'll see is we'll feed in a source code. It will basically give you another source for output, which is the derivative of your. As I said, there are two ways to implement autodiff. One is called operator overloading. One is called source function. We'll start with the operator overloading. So programs execution is traced at runtime to implement. As I said, as you are going along, writing like branching or just doing plain addition or multiplication, at the runtime, the class, if you use PyTorch, let's say, they have a separate tensor class, or if you have used JAX, what they give you is NumPy API. They don't use NumPy as such in the backend, but they give you a NumPy API when they have implemented all of the contract that NumPy has, but in their own way because they want to show the content trace also that the two variables were added, does the derivative differ? So HIPS audit was the team that basically made the differentiable NumPy framework, which was called AutoGrad. This team got more to something, the team of JAX, which is the thing by Google now or something. And then PyTorch, JAX, AutoGrad from the modern framework follow this pattern of it overload. Let's say a custom variable is created, a set of built-in Python variables just to store your trace and add, subtract all the parameters and change of the store. So if you go to Google or go to YouTube, how to implement auto dimension, you'll find this very common pattern that people are creating a very class and doing this thing. Source code transformation. This was just an experimental project by Google. Find the recent papers on it on the Tentative project. It did not become widespread as such, but what Google defines is it is as a source variable derivative in your Python. So your input is a source code, and then they create a abstract syntax tree out of that source code and get the again derivative code of it. Let's say you have a DM function called fx where you are doing x square plus say so you have a x square plus ax. So what you get as the output, so you get a function as output, but you can debug in trace, and you can see behind the scenes actually implementing that backward pass that we discussed about. and send it there. So to find more information where the differentiation actually more machine learning, there's a nice paper, the JML conference. I think it's 18 or something. You can find the state of automatic differentiation and how it started merging into the deep learning. As well as you can go to this my GitHub repo where I have a lot of sources about this topic. I think that's the end of my talk. I'm going to any portion.
All right. Thank you very much. Are there any questions? All right. Well, in that case, let us thank the speaker again, and that ends the session.
Thank you.